Hi everyone. Let's say you wanted to know the rate at which a chemical reaction is occurring, and you're fortunate enough to have it be first order, so it's pretty simple. The rate at which this reaction is occurring is going to be equal to some proportionality constant times the concentration. Here in this example we have our rate, which is moles per second, the concentration in moles, and the constant would have to have units of inverse seconds in order to satisfy this. This is going to have what we call a relaxation time, which we call tau, and that's just going to be the inverse of K, and we'll see how that can be applied later. But for now, we'll see how we can get this in terms of the concentration alone. How does the rate at which a chemical reaction of first order depend on concentration? Well, rate we're saying is equal to moles per second, and moles is concentration. So we can define our rate to be equal to the change in concentration with respect to time. And so we get this equation right here where our concentration is going to depend on time and its rate of change is going to depend on itself. So in order to solve this equation, we're going to divide both sides by this concentration term and multiply both sides by the dt term in order to get ourselves with a separable differential equation. When it's in this form, we can integrate both sides. I missed my integration sign right there. And when you do that, you're going to get this as being the natural log of the absolute value of our concentration. And this is just going to be K is a constant, the integral of dt is just t, and then we have a constant term here, which I called b because we already have a c over here. So this will be b. And we have a k here, so both of your typical constant terms are not usable in this case. So we'll use b. b is that extra constant we put on. So we now will look at how the concentration would be E, because you have to get rid of this natural log sign over here. So that's what we do. And before simplifying it any further, we're going to see what the concentration would be at time 0. So before the reaction occurs, this KT term goes away because your T is 0. So it's just E raised to this B power. And that is what the concentration is at the beginning. So this E to the B power, we're just going to call that C naught, like the initial concentration. And then when you put that back into the equation, when you have exponents that are added together, you can break them apart and multiply them. And this is our C naught, so that's where we get the equation right here. So C naught is our initial concentration. Our C with respect to T that we have right here, that's how the concentration changes with time. T is obviously time, and K is a constant, which should be negative in this case because whatever we're reacting, it's going to be going through an exponential decay, which we see kind of right down here. So as time goes from 0 onwards, our concentration is dropping down in your typical exponential decay pattern. And there's that tau that we were talking about before. Before we get to that, I'll show you something else that we sometimes will show in the math. We have our C naught, and we'll do 1 minus e to the kt. This represents kind of the amount remaining when you're trying to build something up. So in this case, rather than have it where there's a certain concentration that's going down over time, you can have it where there's a concentration that you're trying to use up, and so there's not much, or like, just the amount is what this should be. So the amount that's been reacted, we'll say. It's like this is what you have and it's going down, or you're producing something that's going up to the C naught value. It's just a matter of this 1 minus term right here. This relaxation time is what we define to be either, in this case, it's going to be, might be hard to see here, 0.368. So the point at which it is 36.8% of your original concentration when it's going down. Or it can be the inverse of that. It could be 63.2% of what you are generating in this case. And what these values are is this right here is 1 over Euler's number E. And this is 1 minus 1 over Euler's number is what these percents are approximating. So that's where this relaxation time comes from. So when you're given a first order chemical reaction, you can not only determine how the concentration changes with time, but you can also tell the time at which, what the relaxation time of the system is basically, which we define as being these amounts. So thanks for watching.